Hey, today we've got probability, real fun, right? These are real easy to apply to things, and they're fun to play around with. There's not as much arithmetic here as just logic, so if you like that type of thing. Probability talks about likelihood of an event happening. There's probability when it actually happens, and then there's the experiment, the theoretical probability of something. Like, if you flip a coin, in theory, you got a 1-in-1 chance. It doesn't matter how many times you flipped heads before then, and these are all fun things to imagine and think about. To represent probability, you can range it anywhere from 0 to 1, 0 being impossible, right, and 1 being certain. So it's like 100% versus 0%, and all probability can be measured within those two. Unlikely from 0 to half, and then likely is everything to 1. And, any percent chance really falls under, from 0 to 1. And all the fractions in between. Fractions look like ratios, and a ratio really, for probability, means what we're looking for over everything in the sample space. Okay? A comparison of two numbers with a fraction bar, which means division. Fraction bars represent that operation. Example 1, we're spinning A, B, C, D in that order. Doesn't really matter where they are because theoretically all four have the same possibility. What's the probability the spinner will stop in sector A? Favorable outcomes, there's only one. So we put that on top. And then underneath we say, well, how many are there in the sample space? Right? I count 4 sections. So 1 over 4 is our probability. A or B, now you've got two possibilities. It didn't say A and B in 2 spins. It just said A or B in 1 spin. So now we have 2 over 4. You always want to reduce these. 2 over 4, do reduce that to 1/2. See, our odds are better. Our probability is better now. Well, that's a full 1, right? Because you can't flip it. They're not going to say, well, it's on the line or something like that. No. Then you pretty much have to win every time, which is fun. Probability is expressed as a fraction, decimal, percent, anything that's like part of 1. We can use the word chance when we're expressing it in percent form. For example, 0.25, which really means 25% chance. Instead of saying 1 over 4, we say 25% chance. Odds is where we show it with a colon. Calculate the odds of the spinner stopping in sector A. The odds would be 1 to 4. So instead of showing it 1 over 4 or 25% chance, like with rain and stuff, we show odds with a colon. And probability, again, looks like that. Oops. Looks like that. Or 0.25. Okay, so those are 3 ways we can talk about the same thing. Example 2, if we spin it once, what are the odds it will stop in sector A? Oh, I did this wrong. Instead of 1 to 4, we take 1 and we say, what are all the other outcomes? So they 1 to 3. Because there's 3 that it won't, 1 that it would. That's odds. Ratio of favorable to unfavorable, not favorable to all others. Pardon me. Sample space is a collection of all possible outcomes. We can record it in a variety of ways. Lists, tables, like this one. Looks like what we call in science a Punnett square, where, okay, we're flipping a coin twice. First toss could be heads or tails. Then we make a table with the up and down being second toss being heads or tails. And then you combine options. You can either have a heads, a heads tails, a tails heads, or tails tails. And it shows there's 4 ways that these 2 tosses could go. Sample space abbreviated that way. It can help us calculate because it starts to get confusing when you think about what are all the ways things can happen. When we had odds, we were showing 1 out of, 1 to 3, not 1 out of 3. With odds, it was favorable versus unfavorable. We call this the complement of an event. It's the set of outcomes that we are not including. The complement of getting heads at least once in 2 tosses is not getting heads at least once. The probability of an event and the probability of its complement, you add that up, and that's always equal to 1. Okay? So there's a, there was a 3 out of 4 chance of this. There was a 1 out of 4 probability of that. If we put those together, it's worth 1. The complement is everything we're not hoping to have happen. Really, it's the unfavorable outcomes in my mind. So if a spinner is spun once from up here, this spin, it was this spinner. Keep your finger on that page. Okay, we're spinning the ABCD spinner. Predict, is the probability of spinning A more likely with 1 spin or with 2? Well, you do it twice, now you've got the same thing, right? I guess I can't explain why, but that definitely seems like if you spin it twice, you have a better shot at it, right? Letter B, find the probability of getting A at least once. Probability of getting A at least once. We could do that with the table like they were saying. You could show A, B, C, D on the first spin, A, B, C, D on the second spin, do all the combos, right? A and A, then A and B, and so on. You keep listing these, and then you count up how many of these have an A in it, right? 1, 2, 3, 4, 5, 6, 7 out of 8, 9, 10, 11, 12, 13, 14, 15, 16. 7 out of 16 probability. That's better than what 1 over 4 was, which would have been 4 out of 16. So thanks to this table, I was able to explain why it just seemed like you'd have a better chance trying it twice. And that's exactly the difference. Does that mean it's necessarily what's going to happen? Could I get A on 1 spin and then try again with 2 and not get it at all? Yeah, that's the fun of probabilities. You never know. Find that probability of getting A at least once is letter C. Okay. The probability of not getting A, the complement, not getting A at least once would be all the other ones. 1, 2, 3. I mean, it's going to be the complement. It's going to be 1 minus the one we found. 1, 2, 3, 4, 5, 6, 7. Oh, nope, these are A, so can't count those. 1, 2, 3, 4, 5, 6, 7, 8, 9. Think so. So it's still a lot more likely to not get A, but better chance when you spin it twice. So there's a 9 out of 16 probability of the complement, 1 minus the other option, because it always equals 1. Flipping a coin, this is where you show sample spaces the way I like to do. I like to do tree diagram. When you flip a coin, you have 2 possible options. So you show it like that. And then off of each option, you keep labeling your V's. This set of V's is the first toss. This set of V's is the second, where, okay, we got heads. We could get heads again, or we could get heads, tails. We could get tails, then heads, tails, then tails. And then you label these as your third toss. And you just count up. How many do I have? I've got the heads, heads, heads route. I've got the heads, heads, tails, heads, tails, heads. And this is even showing the order. If the order doesn't matter, that makes it even more likely you get something. Which is more likely, we get heads at least once, or that we will not get heads at least once? Well, this one is 1, 2, 3, 4, 5, 6, 7 out of 8 ways this can go. Basically, we're asking, what's more likely, tails every time or everything else? We're definitely going to get heads at least once, almost assuredly. We use a T-diagram to prove that there's 8 equally likely possibilities, but most of them include heads at least one time. Tree diagram helps us with that. What is the probability of not getting heads at least once? There was 1 out of these 8 outcomes. Outcomes, 8 total. Only one of these doesn't have it. So we use a tree. It looks a little different than the factor tree, right? Because it's lying down this way. Theoretical probability, I think of like what we've been doing, right? We haven't done the event yet. We're just figuring what's the chance. Experimental probability, we determine statistically by real things that have actually happened. Like, in baseball, if they're a 300 hitter, that means they hit it 30% of the time or so. So I use that to determine the future. How many will he hit out of 3? He's going to hit one of them because he usually hits 1 out of 3, or 80% free throw shooter. That means if he's been shooting 80%, that means I expect if he takes 100 shots next year, he should make 80 of them based on what he's already done. That's based on actual things that have happened, not just pure chance, because things like that are controlled by more than just randomness. Emily's a softball player, 21 hits and 60 at-bats. Express the probability that she will get a hit in her next at-bat as a decimal with 3 decimals. Okay, so we find that by saying 21 out of the sample space of 60. Divide that, because that's what this means. Okay, divide it to find the decimal probability. They said to 3 decimals. Well, we have nothing else, so we just add a 0 here. The chance, or I should say probability of her getting a hit next time is 3,500 or 350. So greater than the batting average of the average. This is the batting average of the sub. Who should bat? Is this one better? So this one's better than the sub. You should have her bat. Okay, 350 is a good batting average in softball. Alrighty. Let's do B, C, and F, please. Good luck.